Welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronics supply chain fields. I'm Mike Buetow, Editor-in-Chief of PCD&F and Circuits Assembly. First, a word from today's sponsor. This podcast is sponsored by PCB East, the original conference and exhibition for printed circuit board design, fabrication, and assembly on the East Coast. Visit the website at pcbeast.com for information. My guest today is Matt Wrosch. Matt's a senior product specialist at EMD Performance Materials. An expert in materials science, Matt has held a range of research, engineering, and business development roles in the electronics industry since 1997. He has a master's in materials science and engineering from UC San Diego and a bachelor's from Michigan, which means, as a University of Illinois alum, I'm not sure we should even be talking.
At least you're not Ohio State.
Fair enough. Well, hello, Matt, and welcome to PCB Chat.
Thanks a lot, Mike. Thanks for having me.
So you joined EMD about 4 years ago, which was just after it acquired Ormet, I believe.
Yeah, that's correct.
People might not realize this, but EMD's parent company is one of the oldest companies in the world.
Yeah, that's correct, Mike. EMD Performance Materials is the North American unit of Merck KGaA out of Darmstadt, Germany. We celebrated our 350th anniversary a year or two ago. So it's very the company's been around longer than the country America, right?
Well, happy birthday.
Yeah, thanks.
And you also own Versum, which we visited a few years ago. They're based out of Tempe.
That's right. We just recently went through that acquisition and integration process, or mergers and acquisition, and it's still ongoing, but we are one team now, Merck and Versum together.
Many listeners may know that low melting point solder materials are in vogue right now. Fittingly, our topic today is transient liquid phase sintering, also known as TLPS. So let's start with the basics, Matt. What's the layman's definition of TLPS?
So TLPS is an acronym. It stands for Transient Liquid Phase Sintering. And this is an approach to sintering. It's another sintering mechanism that we've taken advantage of with our paste. And as you say, low melting point is in vogue right now. And TLPS incorporates a solder component, be it a low melting point or high melting point, to help assist with the sintering. So that's where the liquid phase within TLPS comes from.
Years ago, I edited, or really proofread was probably the better term, a dissertation from a good college friend of mine on sintering. But Matt, why don't you describe what the sintering process is, and perhaps maybe talk a little bit about the formulation of the materials that go into these systems?
Sure. Happy to do so, Mike. So with very specific respect to transient liquid phase sintering, what we're doing is taking different powders and different metallurgies. So we have a high melting point powder, typically it's copper, and a low melting point powder, typically a tin-based solder. And we bring those together in a fluxing medium, much like a solder paste. And you take it up to reflow. And what would happen at that point is that the solder component will melt, and it will react immediately with the other powders surrounding it to form a new solid where there is no more melting from that original tin component. So that's the gist of transient liquid phase sintering. It's different from other sintering systems in that we incorporate that mix of high melting point powders and low melting point powders to establish that liquid phase, which with respect to electronics at least, makes it reflowable and a lot more typical to a solder paste as far as how you would use it.
Are the constituents always tin, copper, lead, or are there other, can you use silver, for example, or gold or other materials?
You can. From a cost effectiveness standpoint, certainly copper and tin are attractive from a cost standpoint. However, we have formulations that incorporate silver. We have formulations that are based on tin bismuth versus SAC 305. So sometimes the solder system is different. Sometimes the high melting point metals are different. And it just depends on the goals of the system in general as to how we go about formulating it.
Now, solder paste, of course, is supplied in jars. Is that the same for TLPS systems?
Typically, it's either jars, and we have some formulations that are also dispensable, so they can be done with time pressure systems and needle dispense. But typically, it's a stencil printed formulation.
So users would see a very traditional type of application then using their screen printer and perhaps going all the way down the line to the reflow oven.
Yeah, and it intentionally designed that way. I mean, it's not a drop in 100%. There are different design rules that come up with TLPS versus solder paste, but as far as being able to use essentially your existing setup and existing manufacturing process, that's accurate. The only thing that may differ is that because there's such a large amount of copper powder, we do need a nitrogen environment or some sort of inert environment to keep the oxidation down at temperature. So that's not too uncommon nowadays, even for solder reflow, but that is one of the variances that may be different. Otherwise, it's essentially the same types of stencils, print equipment, reflow ovens that would already be used for solder paste.
So in a convection reflow oven, what would be a typical soldering range of a SAC-like version of a TLPS?
So for us, like a recommended reflow profile would be 40 C per minute up to about 235 C, and then we would dwell there for about 5 minutes. A typical solder reflow profile would dwell at temperature maybe 90 seconds. But because ours doesn't all melt together, we need a little bit more time to drive the diffusion and the reaction to completion. But otherwise, it looks like a typical reflow profile. It's usually just the belt speed's a little bit lower.
Now, it also sounds like they're not always lead-free. You can make a tin lead version of this.
That's accurate. In fact, my background, going back quite a ways now, started with tin lead, and that was military driven. Did a lot of small business research going after thermal interface materials based on tin lead. It's really not a focus at Merck because of the commercial markets. There's only so much utilization of lead, so it's something that we know how to do, but we're currently not offering any lead-based products.
I'm glad you brought up TIMs. I want to get to those in a moment. But let's first talk about what some of the key features and benefits are of the TLPS types of materials. I mean, obviously the low melting is something it's out there. There's a lot of research and literature right now aimed at helping drive down some of those solder temperatures.
Mm-hmm.
It sounds like TLPS fits really nicely inside of that window.
Yeah, absolutely. So we have systems that are based on tin bismuth, which can be processed, fairly low temperatures, 175 C peak temperatures to still not have any melting in a lead-free reflow afterwards. And so we are trying to push the limits of how low we can go to achieve high melting points afterwards. And that is a focus. I would say more of our commercial products are actually based on SAC 305 and still using that type of temperature regime as a goal to replace lead. So a lot of applications are looking to go lead free still, and with high temperature stability. We can do it with tin bismuth at low temperature, but we get better performance with SAC 305 at a slightly higher temperature.
How are the industry qualification and performance standards keeping up? Is there mention of TLPS in there, or would they just fall under other solder materials?
As far as lead free being concerned, or in what respect?
Well, I'm thinking in terms of the performance, like from a J standard 001 standpoint, looking at how the brittleness of the solder joint, the appearance, just any of the criteria that would be used at the end of line to accept the product.
Sure. No, and that's a great question. And one of the challenges we have is with AOI, and the reason being, when you reflow a solder joint, you should get a nice shiny fillet, and it's easy to pick up in an AOI type of system. When we fully sinter our material, it's essentially like a more dark and matte gray type of look. And so there are some visual cues, but nothing that we've been able to establish from a AOI perspective quite yet. It is being worked on at a few places, but that issue does come up because of the difference in color. Our materials also don't flow, and so when I was talking earlier about design rules and some design challenges versus solder, for example, where you're typically used to seeing a fillet form because once all the solder reflows, it'll flow up the metallurgy. With TLPS, it's really net shape. And so as printed and placed and sintered, you don't typically see that same behavior. And so So we do use visual cues, oftentimes related to color, but not so much related to the shape or reflectivity of the fillet.
Does that affect the machine's ability to recognize voids in the material?
No, not so much. Not from an X-ray standpoint. So, I mean, the X-rays that we take are still very clear as far as voiding. We've done a lot of work to do void reduction. So our voids are very small typically in our joints. You can pick them up depending on how you scale your void resolution. However, it doesn't really affect, it doesn't change the density so greatly that X-rays don't penetrate it, for example. It's not a high Z material after sintering.
Yeah, and that's something you know very well, right? Because you worked at Creative Electron, which is an X-ray manufacturer
That's
for a few years.
accurate. Yep.
Yeah. We'll get into the applications in a moment. It sounds to me like TLPS materials share some of the elements of solder paste and conductive adhesives, but they really are a different class of materials. So let's talk about how they differ from other interconnect materials.
So I'm just going to start with solder paste, and I'll try to go down the line of the various materials that come to mind. And if I leave any out, feel free to ask. But let's start with solder paste. So our material, like I mentioned, TLPS is actually composed of typically copper and solder paste, and I would say it's more copper than it is solder paste. So it's more of a conductive paste than it is a solder paste. However, because it incorporates solder, you can process it in a similar way to solder. In that respect, it's similar to solder paste in that, like, you can still stencil, print, and reflow. However, it's different than solder paste in that once you've reflowed and sintered it, it's not going to remelt again. And so you can process our materials one time through the reflow oven and send it through another 10 times, or arbitrary, just picking a number, and it's not going to change. It doesn't remelt. Nothing's going to loosen or shake or lose tolerance because it is solid, and it's pretty much stable up to about 400 degrees Celsius or greater until you start melting those new intermetallics that form. So that's the real difference from solder paste. Now, there are some difference in design rules. Like I mentioned, it's a net shaped material. So as printed, you certainly don't want to overprint. It's not going to come back on itself. Typically, we use a reduced aperture because it's so net shaped. So there are some different design rules from solder paste, but really the key one being, for one, it's lead free if you're dealing with lead solder. Two, it doesn't remelt like a typical solder would, no matter how many times you reflow it. To jump the shark to the other side, if we go to a conductive adhesive, where you've got a curing resin with conductive fillers inside, that'll end up usually being a fairly low modulus material, but some of these new techniques are working on this, but typically thermal transfer and thermal resistance at the interface is high with a conductive adhesive. And with TLPS, whether or not we use a paste or an adhesive matrix, and I mentioned that we have both, the key differentiator between those and a conventional conductive adhesive is that we form metallurgical interfaces with the interfaces. And the thermal transfer is typically an order of magnitude or better than you would get with a silver-filled epoxy, for example. So that's, I would say, the key difference in performance from a conductive adhesive. Like I said, the TLPS adhesives we have are dispensable, so they really are meant to be drop-in for adhesive applications, but the thermal transfer should be significantly better. And then if you look at like a nano sintering material, which may have, melting point depression or very fine nanoparticles that kind of enable that whole process. We don't have any nanomaterials in our process. It's micro type size of powders, and where the very fine nanopowders sort of enable the melting point depression in those systems, we just use a solder paste or solder powder, to achieve that liquid phase and to drive the sintering. Hopefully I touched on everything a little bit. But I would say those are the key differences from the three types of materials that I kind of think of when we're talking about other interconnect pastes.
So the flux system is an inherent part of the material.
Yeah, that's correct.
If that's the case, what's the shelf life like? How does that compare to a typical solder paste?
That's a good question. So these materials are a little more sensitive. We store these at -40 typically, or at least in cold, depending on the formulation. We get roughly 12 months of shelf life at cold. So I don't know that there's a huge difference from solder paste. One interesting aspect of our materials is that once you start using it, you're not going to reuse it like a solder paste. It tends to be irreversible. Once we thaw it out and get it worked on a stencil, we don't recommend, for example, scraping up your excess and putting it in the jar and using it again tomorrow. So that's one of the life differences, I guess you could say, or lifetime differences between this and solder paste. It is a little more sensitive because the copper and tin want to react and the fluxes kind of promote it. And there are some irreversible things that happen. In general, we get good use life on a stencil. We get good shelf life up to 12 months. It's just not quite as gaudy as some of the commercial solder paste that you can, leave out for days and things like that. There's some more environmental protection that we have to keep in mind with these materials.
Well, if you're leaving your solder paste out for days, you're going to have trouble.
You're going to have to, yeah, exactly. Yeah.
Let's talk about the applications here. Are there many TLPS materials in use right now in electronics manufacturing?
Yeah, there's a few that are in use in production. I would say our most mature product and application is within printed circuit boards, and that's using TLPS as vias or as paste vias, and it gives us the ability to do basically anywhere and any layer vias, which for high density applications can become challenging. So we do have a fairly good representation within high-rel PCB, a lot of DoD and aerospace type of work with embedded vias. Our other materials out in the field are die attach and assembly pastes, and those are in qual at a few different places, as die attach in some, as assembly in others, and it really depends on the POR or the material that we're being replaced as to which one we go for.
So we were talking about printed circuit boards. So that must be the material that came from Ormet, correct?
That's correct. We had some historic materials, I guess, that had already been qualled. We've done some work to launch, I guess you could say, version 2 of our PCB materials, which are already being incorporated into flight hardware. So that's been successful, and that's come out of the more recent work and new resources that Merck's thrown at us.
Can you talk a little bit about what the impact is to the designer if they were going to design something like this in? I mean, how does using that, from a bare board perspective, how does using that material change or otherwise impact the way that you would, describe how that board's going to be manufactured?
So it is a fairly big change, and what we're really trying to do is help the designer and the fabricator, with throughput and to limit the number of laminations, for example. So to use the TLPS material within a PCB allows you to basically make your circuitized layers. So as many different active layers as you would need, and to combine them with one lamination step, no matter how many layers there are, with TLPS. And so not only can you put vias in very tight pitch and embedded in places that would be difficult to perhaps get good electroplating, but you can do all this without having to laminate, drill, plate, laminate, drill, plate. It's more or less a build up your circuit layers and then laminate it all at once with as many TLPS vias, and some of these boards are 10,000s of vias inside. And there are some design rules. There's some recommended materials and film adhesives that we would suggest for that. And so that all plays a part. But in general, it's really about bringing it all together with the least number of lamination cycles and the least number of complicating back and forth steps, time limiting steps like electroplating and laminating.
It sounds like if the fabricator knows what they're doing, they could probably have very good control over the process, and perhaps you could have even higher aspect ratio holes because you probably can use a thinner amount of material. Would that be a correct statement?
That is correct. Yep.
TLPS isn't necessarily widely used, but there probably are some ready-made applications out there for it. What would those be?
Well, certainly PCB, like I mentioned, and we have a variety of production projects that we're on PCB. So for the high-rel market, that is a very well-penetrated market, I guess you could say, for TLPS. But then beyond that, really die attach and assembly. So both die attach and passive assembly, and we have different formulations for both. So it's not a one-size-fits-all type of thing. But for die attach applications, especially applications that have either high junction temperatures or are going to see additional reflows. There's real benefit to our materials versus conventional solder paste, or if you're using high lead, that's another place where we're seeing TLPS being used because of the thermal stability. So you don't need to process it at the same high temperatures that you do lead, but it goes lead free and you get the same high temperature stability. So those are a couple places that are being explored. And then certainly gold tin, for example, in high brightness LEDs or other high rel types of die attach markets, the cost of goods are substantially better. And so we've got a formulation that's up to the same thermal conductivity as gold tin, and that's an attractive alternative for that market. So those are some of the applications, I would say. We do have a formulation that is really designed for component attach, and it's designed as an alternative to lead-free solder, and it's meant for applications that go through more than one reflow, and it's specifically designed for that, and it thermal cycles substantially better than SAC 305 in those applications. So that's the field feedback we're getting right now, and I guess those are a little bit of all and everything, right? Die attach, component attach, assembly. There's probably a TLPS for it, and that's where we typically try to recommend is those sorts of applications where there's an obvious benefit or a cost benefit or multiple reflows. If there's no problem with the existing material, then there's no problem. You don't need necessarily something like this, but if you've got some sort of reliability issue or you've got thermal excursions that you're trying to deal with and work around, TLPS makes a very good fit in those applications.
And you don't require any special dispense equipment. It could be used on a standard printer, a standard dispenser.
That's right. It's typical time pressure in-house that we use. We have an auger, so you can do that as well. We don't have a jet dispense version right now, so we don't have anything for jet yet. But no, nothing special, or there's not a very high cost of ownership with this. You don't need any additional materials or equipment that you wouldn't probably already have in your lab.
One area we haven't touched much on is thermal interface materials.
Mm-hmm.
Could TLPS systems be used as an alternative for TIMs?
Yeah, absolutely. TIMs vary, and so it's a huge field. So, if I look at TIM2 applications, for example, in the automotive market, I still see high lead solder. I see nano sintering being used and other things like that, and even phase change materials. So the range is enormous. But yes, we do have materials for that. Certainly our adhesive systems, where it's a little bit lower temperature, fit that bill a little bit better, and then orders of magnitude better effective thermal conductivity than a phase change material, for example. And so there are very real applications, typically high rel or thermally enhanced packages. It's not as cost effective, for example, as like a thermal grease or a phase change material. So it's usually when those materials hit their maximum performance and you need more. TLPS is a good fit for that. And we do actively support and promote into the TIM industry.
Matt, is there anything else you can think of with regard to TLPS that our listeners might want to know?
That's a great question, Mike. Thanks.
It's just a really open-ended one, is what it is.
Yeah, no, I wish I would have had that prepared. Absolutely. These materials are available, and we under Merck have global support, which is not always known, having come from Ormet. And so where we used to be a small operation out of San Diego, now we're part of a 65,000 colleague company with tech service represented in all corners of the world. And so I would make that statement first. But with respect to TLPS, these are very unique, lead-free, high-temperature stable materials. And for next generation applications in wide bandgap semiconductors and in applications that are going to be pushing the boundaries of thermal exposure and resistance, these materials, if your listeners weren't aware of them before, I want to make sure they all know that this is out there, readily available, and very good alternatives to a lot of existing technologies that have probably been played with. And if these haven't been played with, they probably would be a nice fit for your existing process. So sorry, got on the pulpit there, but that's basically what I want to make it known is that these are available, lead-free, high temperature stable, and we'd love to work with you. Feel free to reach out.
I want to just underscore that service part. That's something that, especially in the last year, right? The companies just haven't had the access
Yeah.
that they've been used to personnel, coming in and helping them work their way through something new. And so, as we hopefully this year are able to reopen our factory doors, especially if we're looking at a solution to a problem that traditional solders and other materials can't solve, being able to have engineers come in and help us walk through that, all those hurdles is a big deal. I just really want to emphasize that.
Yeah, no, I agree, Mike. I come from a very small business background. I've worked on SBIRs for decades, and to have this available is new for me too, and it's a tremendous support for our customers, and then that's why I led off with that because I do think that value needs to be kind of brought to the forefront. Merck does have that presence everywhere, and the technical support is out there for these materials in all corners of the world. So yeah, thanks for highlighting that.
We've talked about Merck, we've talked about Ormit, but as I close, I want to remind listeners that if they're interested in more information, they should go to emdgroup.com, where there are videos and matrices showing how and where TLPS materials are used. A big thank you to my guest, Matt Wrosch of EMD Performance Materials, and a reminder that today's podcast has been sponsored by PCB East. Visit the website at pcbeast.com for information on this year's show. Thank you for being my guest on PCB Chat, Matt.
Hey, thanks so much for the opportunity, Mike. Look forward to the next one.
For PCB Chat, this is Mike Buetow. Have a nice day.